So, welcome to this chapter on sound. This is a very interesting chapter where you would know how the police are able to track the speed of a car, or how tuning of instruments is done using a tuner, or even how weather storms and hurricanes are tracked precisely. You would also study about the notes and frequencies produced by a guitar and by a flute and trumpet, etc. So, come on, let's dive into this chapter. First of all, sound waves are mechanical waves, but they are longitudinal waves, and they are caused by vibrating sources. Sound is always produced by vibrating sources, and sound can propagate through a solid, liquid, or a gas. The fundamental frequency or the fundamental formula for velocity of sound is derived from the previous chapter, where we saw that the speed is the product of frequency and wavelength. So here's an example. The frequency is 440 hertz and the wavelength is 0.7 meter. And all you got to do is multiply them to get the speed of sound in the air. Now, of course, the speed of sound changes with the medium, and it is maximum through a solid and minimum through a gas. We'll get to that in a minute. But here's the question: why are sound waves classified as longitudinal? That's because when an object vibrates, it causes the molecules to move back and forth. So if energy is moving along the x-axis, along this axis, the particles are also compelled to vibrate along the same x-axis. And this results in regions where the density is higher. These regions are called compressions, and there are some other regions where the molecules are pulled apart. These are called rarefactions. So that's why sound propagates in the form of longitudinal waves. The next question is, what happens when sound moves from one medium into another? It's important to recognize that for both sound and light, the frequency does not change. The frequency remains the same in all media. So when light travels from air into water, the frequency is the same. Similarly, when sound travels from one material into another, the frequency is the same, but the speed changes because the wavelength changes. This means that if the wavelength decreases, then the speed decreases. On the other hand, if the wavelength increases, the speed also increases. It's also interesting to know that we cannot hear all frequencies. Normal human hearing range is between 20 hertz and 20,000 hertz. Now, frequencies below 20 hertz are called infrasonics, INFRA, and frequencies above 20,000 hertz are called ultrasonics. Now let's look at the speed of sound. The speed of sound depends basically on the elasticity and density of the medium. Actually, it depends on the ratio of the elasticity to the density. As you can see here, the elasticity here is Young's modulus and the density is rho. So speed in solids is the square root of elasticity by density, while in liquids, instead of the Young's modulus, you have the bulk modulus. And in gases, it's totally different. In gases, the speed is given by square root gamma p by rho. Now, gamma is the ratio of specific heats, and rho, this must be rho, that's Greek, or HO. Rho is density, of course. And it's interesting to know that gamma is always greater than 1. It's 1.33 for monoatomic gases, 1.4. Oh, no, actually, it's 1.67 for monoatomic gases, 1.4 for diatomic, and 1.33 for triatomic. You don't have to memorize it, but just know that gamma is always greater than 1. So those are the three formulas for the speed of sound through solids, liquids, and gases. Just to give you an idea of what this looks like, here's a question worked out. Calculate the speed of sound in water. If the bulk modulus is given 2.2 times 10 raised to 9 pascals, and the density is 1,000 kilogram per meter cube. Now, plugging it into the formula directly and calculating gives you 1,483.2 meter per second. That's the speed in water. Now, in air, it's much less. Of course, it depends on the temperature, but it's around 340 meter per second in air. So you can compare. And you can see that the speed in water or in liquids generally is higher than in gases. And in the case of solids, it's even higher. So that's our next question. Could you explain why sound travels faster in copper than in air? Basically, it's because the molecules or atoms in copper are closely packed. So the vibrational mode is transferred quicker because the particles are closer. That's why we say that it's proportional to the ratio of elasticity to density. Copper has a higher ratio for that. And again, the basic reason for having this ratio of elasticity to density higher is because the molecules are closely packed when compared to a liquid or a gas. The speed of sound is also affected by temperature. Generally, as the temperature increases, the speed of sound also increases. Now, why does that happen? We know that the transfer of sound through a medium is due to the particles vibrating. And so at a higher temperature, the particles are significantly separated, so the distance increases, and the random movement also increases. So two things, the separation of the particles are bigger, and the random movement is also higher, and therefore gas molecules move at greater speeds, which leads to more energetic collisions, and therefore the rapid propagation of sound waves. Now, the formula for the speed of sound in connection with the temperature is square root gamma RT by M. Again, gamma is the ratio of specific heats, is 1.4 for air, R is a constant for all gases, 8.314 joule per mole per Kelvin, and T, should remember that T must always be in Kelvin. So if the temperature is given in Celsius, please remember to change it into Kelvin. And M is the molar mass in kilogram per mole. So for example, if it's oxygen, we know that the mass number of oxygen is 32 because it's O2, 16 times 2, 32. But that's 32 grams. So in kilograms, it will be 0.302 kilograms. So keep in mind that it has to be in kilogram per mole. That was just an example for oxygen. So it is the molecular mass expressed in kilograms. So here's a question. Simple and direct. Calculate the speed of sound in air at 20 degrees Celsius. You notice it's a 20 degree. You have to change it into Kelvin. That's why you have 293 here. And because it's air, gamma is given 1.4 times that. And notice that the molecular mass of air is closer to that of nitrogen, because most of air is what? At least 78% of air is nitrogen. And nitrogen has a molecular mass of 0.028. So you can see slightly higher because of the presence of carbon dioxide, which is 0.044. Anyway, so look at that speed that you get, 343 meter per second. So that's how the speed of sound in a gas is calculated when the temperature is given. But there is also an approximate formula which can be used if need be. But again, in this formula, this temperature must be in Celsius, not in Kelvin. Okay. So working out the same problem, you see, this is the formula. It's 331 plus 0.6 times the temperature. Now, 331 is the speed of sound at 0 degrees Celsius, 331 meter per second. So that's where you get that number from. So when you work it out, this is 12, and you get 343 meter per second. So basically the same. Okay, although this formula is an approximation. So if you want the correct, precise results, always use this formula. What's the difference? You have to remember, in this formula, temperature must be in Kelvin, but in this formula, it must be in Celsius. Okay? Brings us to the next topic, the intensity of sound. First of all, we got to define intensity. Intensity is energy by time by area. That's what intensity is. But energy by time is called power. Remember, work over time is power. Therefore, intensity of sound is power over area. That means the unit is watt per meter square. Now, when it comes to a spherical wave, you know that the wave starts from an origin and spreads out in all directions like that. So it spreads out like a sphere. And we know that if you take any 2 points, point 1 and point 2, the power reaching the whole surface area must be the same for both, right? Because the power that starts from here spreads out over the areas. So if you take surface 1, surface 2, the powers must be the same. Now, from this formula, power is the product of intensity and area. So that's the surface area of a sphere. And so when you do both, you get this. When you rearrange, the 4 pi's will, of course, get canceled out. So you can cancel this out. And you get, you get I1 by I2 is R2 squared by R1 squared, showing clearly that the further you go from the source, the smaller the intensity, right? Of course, because sound is spreading out. Now, in connection with this, it's important to know that although the SI unit of intensity is watt per meter square, we use another unit called decibels. And that is because, as you are going to see, human hearing follows a logarithmic scale. Let me explain that. So let's say that you hear a certain sound and then you hear a sound that is 100 times intense than the first one, 100 times intense. But the human ear will just recognize the increase as a double. Wow. So sound is actually increased in intensity 100 times, but to the human ear, it will appear to have only doubled. Where did we get that double from? If you take the log of 100, you're going to get 2. So the log of 100 is a 2. That's where you get it. So the human hearing follows a logarithmic scale. If you take the log to the base 10 of 1000, you get 3. Check it out. So when the intensity of sound actually becomes 1,000 times, the human ear perceives it as being tripled. Now, because of this, is why we are using the decibel scale. Before we get into the decibel scale, you have to know that the smallest sound that we can hear, it's called the threshold of hearing. That's the smallest sound we can hear is 1 times 10 to the negative 12 watt per meter squared. Incredibly small. That's even smaller than the sound of the rustling of leaves. On the upper limit, the threshold of pain, where it technically causes pain in the ear, is 1 watt per meter squared. And this is typically the intensity at which rock music is played. Therefore, caution when you listen to music with especially the earbuds, headphones, remember to keep the volume low because although it doesn't cause pain, day in and day out, when you listen to music at very high volumes, your hearing membrane is being torpedoed with this high intense sound and it slowly weakens. And day by day, you get more and more deaf. You don't realize it because it's gradual. So please play music at a low volume. Now, here is the formula where you change the intensity into decibels. So beta is the intensity of sound in decibels. And the factor 10 comes in because of the word deci. See, deci means 1/10. Anyway, so it's 10 times log to the base 10 of this ratio, where I naught is the threshold of hearing. So you have to know this number. I is any given intensity. So here's an example. Look at the table. If you have I as 1 times 10 to the negative 12, now you have both as the same. So the ratio is 1. And log to the base 10 of 1 is a 0. That's why you got 0. On the other hand, if this is 10 raised to negative 11, then you're going to get this ratio. And then when you take the log of that, you're going to end up, this ratio is going to be 1. And 1 times 10 is 10. So on and so forth. So it's interesting to look at the threshold of pain right here. 1 watt per meter squared, which translates to 120 decibels. And that's at what rock concerts are played. And it's also the intensity produced by a pneumatic chipper at 2 meters, produced by jet planes, I think at 30 meters from it. That's why, oh, nope, actually jet planes at 30 meters cause severe pain. And it's 140 decibels, and it can damage your eardrum in seconds. And then 160 decibels, physically, the eardrums can burst. So that's about the intensity of sound. Now, before we work out this problem, I want to tell you that when sound propagates through a medium, because of compressions and rarefactions, I hope you remember that term, where the density becomes higher at some regions and lower at some other regions, there is a fluctuation in pressure, right? And so these are called pressure waves. And the pressure wave can be modeled with a sine or a cosine, as we've seen in the last chapter. And it's exactly the same function as given, where you see delta P is 1.20. Now that's the unit pascals. Sine kx minus omega t. You may remember this from the last chapter. So in this problem, a sound wave is modeled with that equation, and sound travels at 343 meters per second. First question, what's the wave number of the sound wave? So wave number is k. So we're going to find k. Then what's the value of that pressure or change in pressure at x is 3 meters and t is 20.00 seconds? Okay, so if you recognize this as omega, omega is in radians per second, then from the last chapter, we know velocity is omega by k. Rearrange that to find the value of k. Take note of the unit. It's radians per meter. So that's how you find the wave number. Okay, k is the wave number. And then for the b part, just substitute the value of x and t into the given equation, which I have done here. Since we got the value of k, that's x, omega, t. And this is 549.3. This is, all right, that number. And then, so remember that this whole thing is the phase of the wave. So I called it theta, where theta is kx minus omega t. And I found the number. It's a negative. And then when you take sine of that, you get negative 0.924. And then when you multiply that with 1.20, which is 1.20 here, you get minus 1.10 Pascal. But it's important to know how we get sine theta as negative 0.924. You can enter it into the calculator, but remember that simple harmonic motion or oscillation is equivalent to circular motion. So some particle may start from here and may have completed just one rotation and reached here, or may have completed two rotations and reached here. We are not interested in how many rotations it has completed. We only want to know the angle. So since we know that each rotation is 2 pi radians, we divide the entire thing, the entire angle, with 2 pi, and that's how you get theta. Check it out in your calculator. That's how we get this number, is what I'm trying to say. Okay, so that's about pressure waves. Here's another one on the same lines. Here it says, consider a sound wave modeled with the equation xt is equal to 4.00 nanometer cosine that. So it should have been here. There's no space. So once again, you realize k, omega. But you have to find the maximum displacement. And what's that maximum displacement called? It's called amplitude. Now, amplitude is right here. Okay? And then k and omega. To find the wavelength, we have to remember that k is 2 pi by lambda. K, wave number, is 2 pi by lambda. Again, from the last chapter. So lambda is 2 pi by k, and you get 1.72 meter as the wavelength. To find the frequency, which is f, We can do that from omega because we know omega is 2 pi times the frequency. So we have omega here. Rearrange that to get the frequency as 200 hertz. Excuse me. And once you have the omega and the k, speed is the ratio of those two quantities, and we get 6.34 meter per second. All right. Now, here is a question that could be very important for the exam. Because when you deal with decibels, you should know how to convert it back and forth. I mean, to change from decibel into watt per meter square and the other way. So 10 cars in a circle at a boombox competition produce 120 decibels sound at the center of the circle. Question is, what is the average sound intensity produced by each one? So 10 of them produce 120. How much does each one produce? The answer is not 120 divided by 10. No, that would be most incorrect. So to work out this question, first you have to change decibel into the proper unit, which is watt per meter squared. So that's what is done in this step if you look at it. So this is the formula. Beta is 10 log to the base 10 I by I naught. If you rearrange that, you will get this. And how do you get that? If you take log on both sides, you are going to get, you know that 10 raised to something is the opposite of log to the base that. So when you say log to the base 10 on one side, on the other side it becomes 10 raised to. So that's why, first of all, you divide both sides by 10, you're going to get beta by 10 is equal to log base something. Now, instead of putting that log there, you could put 10 raised to beta by 10 on the other side and get rid of the log. That's what I've done. So I by I naught is 10 raised to beta by 10, from which I naught is the threshold of hearing, which you have to remember, and beta is 120, so 120 by 10 is 12, so 10 raised to 12. Now these two cancel out and you get 1.0. So that's produced by all 10. Therefore, for a single car, it would be that divided by 10. So once you get it into the proper units, you can divide it by 10 to get the intensity of a single car. And then you have to turn it back into decibels, again using that formula, which I've done. So beta is 10. Look at that formula, I by naught, and I is 0.1. And do the math carefully, you're going to get 110 decibels. Isn't that interesting? 10 of them produce 120. Look at that. A single one produces 110. So this is 10 times, it's not 10.11. So 10 produces 120, 10 playing together produces 120, but a single one produces just 110. It produces 110 all on its own. Keep that in mind. And a similar question, a person has a hearing threshold 10 decibels above normal at 100 hertz. See, we don't hear or we don't perceive all frequencies with the same intensity. So this person can hear 100 hertz at 10 decibels, and 50 decibels is what he hears 4,000 hertz. So he hears the higher frequencies at a bigger intensity. So he can hear or he can perceive higher frequencies louder. That's why in music systems, you have a control over the frequencies. You can adjust the loudness because you want to hear all frequencies at the same intensity. Okay. So that's what this question is saying. How much more intense must a 100 hertz tone be than a 4,000 hertz tone if they're both barely audible to this person? All right. So to make it heard at the same intensity, surely the 100 hertz one must be at a much higher intensity. We're going to find that. Now, to do that, this is the formula again, same formula. And then you have the difference here is the same difference. You can see I've just plugged it in. So you got I 100 here, I intensity at 100, intensity at 4,000 there. And then you know that log A minus log B is just log A divided by B. So the 10 is taken out, and then the I naughts are going to get canceled out when you divide. And that's why you get I 100 by I 4,000. Okay, again, log A minus log B, log A minus log B is the same as log A divided by B, okay, which is what I have done. So when you substitute, we know that this is 10, this is 50. So right there, 10 minus 50, and then that's negative 40. Divide both sides by 10. You get that, and that's negative 4. And then just like before, instead of log to the base 10 here, you could put 10 raised to negative 4. And that's how you have that. So that's our answer. So that means the intensity of the 100 hertz is much smaller. You can see it's 1 by 10,000. This is 1 by 10,000. So if you want to hear the 100 hertz at the same intensity, then it must be 10,000 times more intense. I hope that makes sense. All right, now we move on to the interference of sound waves. So when two sound waves propagate through the same space, they are superposed on each other. And so they interfere. The interference can produce cancellation at some points, which is called destructive interference, and can produce an increased sound at some other points, which is called constructive interference. So when two sound waves move through the same space at certain points, they support each other, increasing the intensity, and at some other points, they cancel out. Now, to get the mathematics, if you look at this diagram, you can see two speakers here, 1 and 2, and sound waves are reaching this point P. But although the sound waves produced have the same wavelength, the two speakers are said to be coherent. That's the word. Coherent means the same wavelength. And if they produce the same wavelength at P, because P is at a smaller distance from the first speaker compared to the second, what is going to fall here at this point could either be a crest or a trough. Now, as shown in this diagram. So if you look at the central point between the two, look at this. You can see that it's either two crests coming together or two troughs coming together, two crests or two troughs. So that produces constructive interference. So they support each other. But if you look at this point, look at these points. At these points, you can see that it's a crest and a trough, a crest and a trough. See? A crest and a trough. So the crests are given by the dark lines and the troughs are by the whiter lines. So here you're going to get destructive interference. So if somebody's situated here, between these two speakers, somebody is seated here, that person will not hear any sound. Same here, if they are seated here, they won't hear any sound. But for this person, people seated at these points, they will hear maximum sound. This is so important in an auditorium where several people are listening to music and seated at different points. We have to make sure that such a thing does not happen. That is why, the walls of the auditorium are covered with sound absorbing materials, because otherwise, the sound from the orchestra can go directly to that person and also get reflected from a wall. That means sound is reaching the person along two different paths, causing interference. So that should not happen. Okay. So getting back to that story, with math, you can say that because of this path difference, path difference means the difference in the distance. The path difference causes a phase difference. Okay. So if the first wave is represented by this, oh, the first wave is represented by this, and the second wave by this, you see everything is the same. The amplitude, k omega, same, except that the first wave is having an additional angle. So there is a phase difference between these two waves, and the phase difference is phi, right? So using trig, when you add two sine functions, so sine A plus sine B, you will get this. You will get 2a cosine phi by 2 sine kx minus omega 2 plus phi by 2. And that's because sine A plus sine B is 2 cosine A minus B by 2 times sine A plus B by 2. Look at that. Look it up. Sine A plus sine B. Look it up. And that is different from sine A plus B. Okay, that's different. So we need sine A. So this whole thing is A. This whole thing is B. So coming back, the path difference between two waves can produce a phase difference. And it can produce constructive interference or destructive, depending on the point where the person is. If the path difference is an integral multiple of the wavelength, so if the path difference is n lambda, then you get constructive interference. Let me explain that. That's because if a crest from this, let's say it's a crest here, that is what, the fourth crest? And let's say it's the fifth crest from here that falls here. So it's the fifth crest and the fourth, it doesn't matter. As long as it's a crest and a crest, you get constructive interference. But because there are 5 here and 4 here, the difference in path is a lambda. Or it could be the 6th one from here, like 6th one, and the 4th from here. Now the path difference is 2 lambda. So whenever the path difference is an integral multiple of lambda, you will get constructive interference. But if it's right in the center, like if the point is here, the path difference would be 0, right? That's why it starts with 0. If the path difference is 0, again, you get constructive interference. Now for destructive interference, it's always a crest falling on a trough, right? So it would be a crest from here falling on a trough from the speaker. And that means the path difference is lambda by 2. And this is generally written like this. Path difference is 2n plus 1 lambda by 2, because when you give the value n is equal to 0, this whole thing becomes 0 and you get lambda by 2. See that? If it's 1, then you get 2 times 1 plus 1, that's 3. So you get 3 lambda by 2. So you either get lambda by 2, 3 lambda by 2, 5 lambda by 2. All these path differences produce destructive interference. So that is about the normal modes of a standing sound wave and sound interference. Now, to show that, here is a question. At a location that is 3 meters from a wave source A, that should have been caps A, and 4.20 meter from wave source B, destructive interference occurs. So it's 3 meters from one and 4.2 meters from the other. Sources A and B are coherent. See that? It means same wavelength and in phase. So that means when they are produced together. That's what it means. What is the maximum wavelength of the waves? Okay, path difference is 1.2 meter for sure, this minus this. And because it says what's the maximum wavelength, we're going to go with the condition for destructive interference, which is 2n plus 1 lambda by 2. You may say, why? Because for destructive interference, you know the path difference is lambda by 2, but for the other one, it's lambda, right? So this is less. Since you're looking for maximum wavelength, that means the path difference should be the smallest. So that's why we're going with 2n plus 1 lambda by 2 is 1.2. And what's the smallest value of n? 0. So that means lambda by 2 is 1.2, so lambda is 2.4. So if the wavelength produced by these two is 2.4, this person here is going to hear no sound at all. That's what this problem shows you. Oh, interesting. Noise cancellation headphones, how do they work? Well, it picks up the noise, which is not the music, might be the roar of a jet engine. So you're trying to listen to music on an aircraft. So the microphone picks it up, and the electrical circuit produces a wave that is exactly opposite in phase. Look at the diagram. So this is the noise, the red one or the brownish one, and the electrical circuit produces something which is totally opposite in phase. So when this noise is at its maximum or a crest, the electrical circuit produces a trough. So they cancel out. At every point, they cancel out. So the incoming noise, the second sound which is introduced, together they cancel out and there's nothing, it's silence. Isn't that interesting? That's how noise cancellation headphones work. All right, that brings us to the vibrations of air columns and pipes. Here we're talking about wind instruments. We're considering a closed pipe, which means one end is closed and the other end is open. Now, if both ends are closed, it's useless. So even when you say closed pipe, one end is open. Now, the simplest wave form, and we're talking about standing waves here. The simplest standing wave, as you can see, that's produced here. That's a complete wave, 2 segments. If you remember last chapter, you can produce it this way, where the antinode, which is the maximum vibration, the antinode is exactly at the open end. When the antinode is at the open end, that's when you hear maximum sound. Now, do remember that these are longitudinal waves, so the particles are trying to vibrate to and fro like that. The particles here are air molecules. Now, since this is closed, there's no way for air molecules to move. That's why at the closed end, you always get a node. Now, at the open end, you could get this part, any part. But if the length of the pipe is such that you have an antinode at the open, then this air column inside will resonate with this tuning fork. So this tuning fork is playing, and if you keep your ears close to this open end, you can hear a loud sound for a certain length. So we say that these two instruments are in resonance now. Okay. From the diagram, this is lambda by 4. It's 1/4 of a wavelength, because this is a full wavelength divided into 4 parts. And so that's where we get this is 1 by 4 lambda 1. But again, you can, if you increase the length, you could get to a length where you once again get maximum sound. This length, see that? This is an antinode again. So when you hear that, that's called the next harmonic. In the next case, the length is equal to 3 by 4 lambda by 2 because you got 3/4, you see? And so on and so forth. Next one would be 5 by 4 and so that way. Okay, that's what is shown here, lambda 3 plus. So the fundamental frequency happens when lambda 1 is 4 times the length, right? Yeah, because L is 1 by 4 lambda. If you rearrange that, you're going to get lambda is 4 times the length. And then because frequency is velocity by wavelength, remember that formula? Frequency is velocity by wavelength. You get that. So if the length of the pipe is given, and knowing the speed of sound in air, you can calculate the fundamental frequency. The word fundamental here means the smallest frequency. The next one is called the first overtone, and the first overtone is the third harmonic because it's 3 times this. Look at that. That's why it's called F3, third harmonic. The second overtone, so the overtones are numbered sequentially, like first, second, third, but the harmonics go with what number? Look at that. So the second overtone is the 5th harmonic, and the third overtone is the 7th harmonic. I think you understand that. A clarinet is a closed pipe instrument, but it's important to notice that you only get odd harmonics here, 3, 5, 7. And also, when we look at an open pipe where both ends are open, you will see that the fundamental frequency here is lower. And then we have this important formula, 2n minus 1 lambda by 4 for n is equal to 1, 2, 3. So if you put n is equal to 1, you will get lambda by 4. N is equal to 2, you will get 3 lambda by 4. Now, this is why the clarinet is rich and woody in the tone. It gives a deeper pitch. Pitch is another word used for frequency, remember that. And that's in comparison to open pipe instruments of similar size. Okay. Now, the same kind of reasoning for an open pipe, the only difference is that here you could have antinodes at both ends. Now, because of that, this is half a wavelength, right? And the next one would be again one more from there. So you will see that lambda here is 2 times the length, which gives the fundamental as velocity by 2 times the length. The first overtone is going to be actually, I would have loved for this to be written as 2V by 2L. Same thing. And so it's 2 times. So the first overtone is second harmonic. The second overtone is the third harmonic. The third overtone is oh, that's a mistake. So it should be 4 here. Sorry for that. F4 is 4V by 2L. Yeah. So what do you notice? You notice that an open pipe produces both odd and even harmonics. So which of these is a better musical instrument? It's an open pipe because it produces more frequencies, so to say. So here's a question. What's the fundamental frequency of a pipe open at both ends? The length of the pipe is given on a day when the speed of sound is also given. What is the fundamental frequency? It's open, so we know lambda is 2 times the length. Once you get lambda, frequency is speed by that wavelength, so the fundamental is 256 hertz. The B part, what is the frequency of its second harmonic? Since it's open, just multiply it by 2. That's it. What is the frequency of its third harmonic multiplied by 3? Right? Isn't that simple? It is. Now, a real-life application of resonance in an open pipe is a flute. So read that, and we know that this is the formula for length. Both ends are antinodes, so both even and odd harmonics are harmonics are produced. That's why it produces a smooth sound. It shouldn't say bright, it should say rich, smooth sound because of both even and odd harmonics being there. All right, here's a question. A nylon guitar string is fixed between two lampposts. So we looked at vibrations of guitar strings in the previous chapter. So we're trying to combine both chapters here. And the length of the string is given, the linear density is given in gram per meter, and the tension is given. The string is placed next to a tube open at both ends. And so the string is plucked and resonates at the fundamental frequency, while the tube resonates at the end is equal to 3 mode. So what is happening is the guitar string is plucked. That creates the air column in the open tube to vibrate. So both are vibrating at the same frequency. Now, what is the length of the tube? Okay, let's do it. Now we know for a guitar string, velocity is square root T by mu. So plug in the tension and mu. Remember, mu has to be in kilograms per meter. So that's why you have times 10 to the negative 3, because that was gram. And that gives you 149 meter per second. Then the fundamental frequency of the string is speed by 2 times the length. Excuse me. That gives you 37.3 hertz. So that's for the string. For the open pipe, we just did see that this is the formula. And solving for the length, for the third, you get, and you know it should be 37.3 because both are playing at the same frequency. And just plug it into this formula. N is 3, velocity given in air, 2 times the length. We're looking for the length. Solve for the length and you get 13.8 meter. So if the length of the open tube is 13.8 meter, it will resonate. So now we know that in a flute, you change the length actually by opening and closing the holes. You change the resonating length. That's how you get it to produce different frequencies. The flute being an open tube, okay? All right, beats. Beats is an interesting phenomenon. This is again caused due to two sound waves interfering, but the important thing is to know that beats are produced only when the sound waves are slightly different. The frequencies are slightly different. See that? So if one is playing at 256 and the other is playing at 252, then you're going to hear 4 beats per second. Now, what is a beat? Remember, I said 256 and 252. A beat is a maximum and a minimum taken together. So if both of them are playing, you're going to hear sound something like ooh, ooh. So you're going to hear a maximum and a minimum, constructive and destructive. So that's why it says, instead of hearing 2 separate tones, the listener perceives a single tone that fluctuates in loudness. This rise and fall is called a beat. Okay, so I've already explained how beats are produced, and here is a diagram that shows you clearly what is happening. So you have the red and the blue waves, slightly different in frequencies, therefore they're slightly different in wavelengths. They start off together, but you can see they soon separate. You see that? They soon separate. So here the crests are together, but next time the crests become together is here. You see? In between, The crust from the blue is falling on the trough from the red, so cancellation there. So you have complete cancellation, so that's destructive. You have constructive, again destructive, constructive, so it keeps going. And it happens at regular intervals, as you can see. Now, this is the resultant that's produced. Again, as you can see, they cancel out and there's a maximum, okay? Clearly labeled, destructive, constructive here. And mathematically, you could either take it as a cosine or a sine. So I'm using cosine here. So if y1 is given by this, y2 is given by this, notice that their frequencies are different. Wave numbers are surely different. But I just consider the amplitudes to be the same, which is what the diagram shows. Their amplitudes are the same. Do you see? And cosine u plus cosine v. So this is u, this whole thing, this is v, is given by 2 cosine, sum divided by 2, cosine, difference divided by 2. When you use that, you're going to end up with this. Now, a is taken out right there, and you're going to end up with a sum and a difference. Oh, therefore, you end up with 2a cosine 2 pi f1 plus f2 by 2 and f1 minus f2 by 2. So you get that. So you see that the amplitude, what's the amplitude of this wave? I think I should highlight. This whole thing is the amplitude of the wave. Do you see that? This is the phase. So a wave has an amplitude and a phase. Now, in the two interfering waves, the amplitudes were the same and constant. It's not changing. See, each time they get to the top, it's the same. But for the resultant wave, the amplitude is changing. You can see it's decreasing, becomes 0. That's because in this term, this whole thing is the amplitude. In this term, you got an angle. Cosine 2 pi f1 plus f2 by 2. And you got the time factor. So with time, it's going to change. Correct? And also with x, it's going to change. So this is that x is equal to 0. But if you look at different points, you start giving different values for x, you will see that at some points it'll cancel out. So the amplitude fluctuates, but the frequency at which it fluctuates is given by f1 minus f2 by 2. So the by 2, that's half. It's from going from one minimum to the next maximum. Remember that together they're called one beat. So now you'll have to multiply this 2 to get the beat frequency is f1 minus f2. So looking at this diagram, what's the beat frequency? If you look at this timing, you see it's 0.03 here and 0.06 here. So the difference is 0.03 seconds. That's the difference in time, right? So frequency would be 1 by 0.03. And then you got to multiply it with 2. So it'll be 2 divided by 0.03. Okay, where's my calculator? 2 divided by 0.03. That gives you 2 divided by 0.03 gives you 66.66. So here's the question that I think we did something similar. Once again, a string is in resonance with a tuning fork, but beats is also introduced, okay? So mu of the string is given, the length is given, tension is given. And we know from there you can get the speed of a wave in the string and then get the fundamental frequency, which we did before. But the second part talks about a 1024 tuning fork and beats 52.83 between the two, between the string and the tuning fork. So what are the possible frequencies and wavelengths of the wave? So now we already got that for the string. That's the fundamental frequency. But now for the tuning fork, we do know that the frequency of the string minus that of the tuning fork. And do you see this? Because it could be plus or minus. So we take the absolute value, okay, is 52.83. So this frequency of the string could be higher than this by that much or lower. Okay, I hope that makes sense. So the frequency of the string, when you bring it to the other side, is plus or minus that. So it should be either this or this. Once you get the frequency, you can find the wavelength using lambda is from this equation. You see that? And so you get these wavelengths. So that's a combination problem where you combine. So that could be important for an exam because you have strings in combination with a tuning fork, and then you also bring in beads. So that's a good question to test if a student has understood all of these three concepts. Well, we finally come to the last topic in this chapter, which is called the Doppler effect. So the Doppler effect is, could be explained with a diagram here. So you have a source of sound, the car honking or the horn blowing. And if you have two people at rest, they're not moving, then, and the car is also not moving. So the source is not moving, the listeners are not moving. You can see that the wavelengths reaching both of them will be the same because the distance, it is the same. So whatever frequency the driver of the car will hear will be exactly the same heard by these two listeners. On the other hand, if the car is moving towards one and away from the other, the wavelengths become shorter here, as you can see, because it's moving towards, meaning the frequency will become higher. Remember, frequency is speed by wavelength. So when this becomes lower, it becomes higher. So Y will hear a higher frequency than the driver of the car. X will hear a lower frequency than that heard by the driver of the car. Now, the same thing can happen if the source is at rest and the listeners are moving. See that? Same thing can happen there. So you have all kinds of scenarios here represented. And to get the formula, just from the above diagram, you can see, but we have to know that this is the speed of sound waves. This is the speed of the source. And this is the speed of the listener. So we'll just focus on one of them. We'll focus on X now. What happens to the wavelength perceived by X? It increases. You can see as the source moves away, the wavelength is becoming bigger because it's taking more time. So the difference in wavelength heard by the observer, so O here stands for observer, could have been listener too, okay, is the actual wavelength of the source plus at distance, increased distance because of the motion. How do you get distance? Distance is speed multiplied by time. Okay, so speed of the source multiplied by the time gives you that distance. This again is speed of sound multiplied by the same time. So this is speed of sound multiplied by time it takes to reach the source, the time it takes to go from the source to the listener. That's this time. And then the math shows you that 1 by time is frequency, right? So instead of time period here, you can put by frequency. That's what it's done. And then because you have the same frequency here, you take it common, add the two, rearrange to make frequency heard by the observer, the subject, you will get this formula. And it's very clear that since this denominator is bigger, the observer is going to hear a lower frequency than this. So, in other words, this is less than 1. On the other hand, if it's y, you have the opposite. So the frequency is, now you got to take the distance as minus because the distance is becoming smaller. And then doing the same thing again will give you, instead of a minus, it'll give you, instead of a plus, it'll give you a minus. So here it was a plus, here to be a minus. So you could put both the formulas together like this. In the denominator, just put minus or plus. Remember that minus is when it's towards the observer, plus is when it's away from the observer. So all of that I have combined into a table here. So the source is stationary, the observer is stationary, no change. See that? And then what we did was the source moving towards an observer and towards the observer. So we're talking about y here. See that y? This is moving, this is source moving away from the observer. That was the x. This was the y, because the observers were stationary in both cases, right? You understand? But what if both were moving? Okay, source moving towards the observer and the observer moving towards the source, then you got to add the speed of the observer in the numerator. On top of this, see that? You just have to replace this. Let me show you this with this. If it's away, then instead of plus, you have minus. So you have to understand how to use this formula and where to use it. But the most important thing is to remember that if the source is approaching the observer, the frequency appears to have increased. If the source is going away, the frequency appears to have decreased. So I have that fundamental idea and you should be able to do it. So here's the problem. A commuter train blows its 200 hertz horn as it approaches a crossing. Speed of sound is given. An observer waiting at the crossing receives 208. So you see, the observer is hearing an increased frequency. What's the speed of the train? What frequency does the observer receive as the train moves away? Okay, so that's the second part. In the first part, this is the formula. So the FO is just F prime here, same thing. You could replace that with FO if you didn't like it. Okay. FO is that substitute and calculate, carefully calculate, solve for the velocity of the source. It's a lot of math steps, but you will get 12.88 meter per second. So what's important is to understand what to plug in each of those for each of those variables. Now, as it goes away, you see the formula changes from the minus here, it becomes a plus. See, that's the difference. And therefore, the frequency heard will be 192.6. So the actual is 200, approaching it's 208, going away it's less. Notice that the difference is not the same, okay? So it's not the same, it's not symmetric in that sense. So that's a problem on Doppler effect. Here's one more. Two eagles fly directly toward one another. The first at 15 meter per second, second at 20. Both are screeching. The first one emits a frequency 3200, second one 3800. What frequencies do they receive if the speed of sound is 330 meter per second? So here, the two eagles function both as the sources of sound and as observers. So you have to take one at a time. So here is the complete Doppler effect equation. And in each case, frequency received by eagle A, who hears eagle B. So eagle A is taken as 3800 hertz. The observer eagle, which is eagle A, moving at 15. Okay, so you see that because he hears B, you take that frequency produced by B, but this is the speed of eagle A. And then the source speed is 20 meter per second because the source is eagle B. Okay, don't get confused. Look at it carefully. Plug it in, and then you get this as the answer. Now, doing it the other way, 3200 is the frequency produced by A, and A is moving at that. No, A is moving at that speed. The observer is moving at that. So when you plug in the numbers, you get that. It's easier said than done. You have to be very careful at what you do. So here are some applications of Doppler ultrasound, Doppler effect actually. The first one is Doppler ultrasound, where high frequency waves are used to measure the flow of blood through arteries and veins. And it can be used to diagnose blood clots and heart valve defects and all that. So how does it work? A transducer sends out ultrasound waves into the body, which is reflected off red blood cells. And depending on how the red blood cells are moving, the frequency would be higher or lower. Toward it be higher. If the blood cells are moving away, it'll be lower. And then you also can find the change in frequency and relate it to the speed and direction of blood flow. So you can actually calculate the speed at which blood is flowing based on the received frequency. And that is the basic equation. And this is very important because it's non-invasive and helps save lives. So that's one. Second is how the police use this Doppler effect to measure car speed. Okay, so radar guns are used. And again, it works on change in frequency because the gun now emits radio waves, which is an electromagnetic wave. We look at that, and these waves bounce off. And if the vehicle is moving toward, it's a high frequency, away, it'll receive a lower. And the most important, that measured change in frequency depends on the speed of the car. So you can directly correlate these two using the equation. Now, this is a simplified equation, and it's only used when the source and detector are stationary related to the Earth. The cop's gun is the source as well as the detector. It both sends out waves and receives it back. So only in that case can you use this. Please don't use it in other cases. So this is directly the frequency shift, and then that's the speed of the car. And the factor 2 comes in because of the reflection back and forth. So that's why 2 comes in. Okay, so that's an application of Doppler effect. Storm tracking. How is this done? You read this, but basically it's by tracking the speed of water drops. We can know if it's moving in or moving out, and you can calculate the speed too, again based on the change in frequency. So the radar uses Doppler shift, which is the change in frequency, to calculate the speed and direction of precipitation particles. So raindrops, snowflakes, or hail, which is a part